Okay, we'll be starting section 1.6 today. Here's the learning targets we'll be dealing with in 1.6. I can identify and graph linear and quadratic functions, along with cubic, square root, and reciprocal functions. We'll work on all those today. We're going to wait on the step and piecewise until Monday. And recognizing graphs of parent functions is kind of part of this, identifying these different families of functions. Okay, let's start with the most basic and something we've been reviewing all year so far. Anyways, here's some of the equations of linear functions we've seen: slope-intercept, point slope, in either general or standard form. All right, the constant function. If we have f of x equals c, just some type of number, right? Or I can even write that in here, right? Another version. Y equals some constant number, we get a horizontal line. So that's why they call it the constant function. It's constantly whatever this number is. Like this one looks like it's around 1.5. It's constantly at 1.5. Okay, so the constant function. I made note here too. This is when m equals 0, the slope. Okay, so these are just two different types of linear functions, or a subset. The identity function, this is written kind of lightly, so maybe you want to write it like this: y equals x, or f of x equals x. The identity function just means that, right? It's going to have, when x is y, what type of coordinates make sense? Like 1, 1, 2, 2, 3, 3, -5, -5. As long as they're equal, they're going to land on that line right there, and we call that the identity function. Okay, slope is 1, y-intercept is 0. Okay, just some review characteristics too that we know about linear functions. The domain and range both are all real numbers. Of course, we know when the slope is positive, it increases from left to right, and it decreases when the slope is negative. Okay, and some other things there. All right, let's go ahead and move on to this first example, and then the next page is some other parent functions. Write the linear function f that has the given function values. Sketch the graph of the function. Okay. Well, let's use some function notation skills first to grab some points. What I mean by function notation is making sure you understand these input and output values. Okay, to put that right below kind of lines it right up for us, right? The input value, or x, is 1. And the output value, when you plug 1 into this function, the output value is -5. So we can make some coordinates pretty quickly by using that format. Okay, so we're going to write the linear function that has these given function values right here in these order pairs. So it's just presented a little bit differently, but we've done these skills before. It's on your last test, right? To write an equation of a line now, we're going to want to find the slope. So 4 minus a -5, so we're going to have to do +5, and then 4 minus 1. Okay. All right, so using this slope and one of these 2 points, we can write an equation of a line now, okay? So y minus, I'll use this one here, 4 equals m times x minus 4. Typically, we like to solve this for y, so go ahead and distribute the 3. Okay, so we get 3x minus 8. Now, don't be surprised if they write this in function notation in the back too. You need to make sure you know how to read both of these. They may write this as f of x equals 3x minus 8. Okay, we're going to treat those solutions the same. All right, so that was kind of part A, write the linear function. Part B, sketch the graph of the function. Now, we usually like to go right to the y-intercepts of -8. It's kind of off the graph here, so we might not want to use that strategy. Since we're given 2 points, we could just plot these 2 points and draw a line between them. So 4, 4, 1, -5. Okay. Connect them and then draw a line to show that the domain and range keep going. Any questions before you try it? Okay, I'm going to pause. You try number 2, and then I'll give you feedback. All right, here's the coordinates we need to form from this function notation. X, output value y. All right, so our slope ends up being -1. -1. Now grab one of these points. Now, if you chose a different point than me, this step looks different, but once we both solve for y, they will be the same. So here's your final answer. Y equals -x plus 2. Okay. All right, now this one, the y-intercept of 2 is a little more in range of this coordinate plane over here. So that's the approach I took. I started at 2, and then I have a slope of -1. So down 1 and to the right 1. Okay, to get that going. Okay, let's go ahead and take a look at the parent functions now on the next page. We really just dealt with linear so far and some review. There's another resource too on page 61 of the book. If you want to reference that, go ahead and write that down. All right, so parent functions. You think, what does a parent function look like? Well, if you don't have any multipliers or any constants being added or subtracted, if it didn't have any of that, what would it look like? It'd be pretty plain. Okay, so once again, it's kind of light. You might not be able to read that. It says f of x equals absolute value of x, or simply put, just y equals absolute value of x. That is the parent function for the absolute value function. Okay, domain and range, but sometimes these change if we start shifting it around in section 1.7. We'll be doing transformations. All right, so mainly just focus on the shape. You don't necessarily have to memorize all these. Just got to be familiar with some of the characteristics, and the characteristics should show up in your graph. For example, domain's all real numbers. If you put arrows on your absolute value function, you just demonstrated that. Okay, makes sense? So focus on the shape with these parent functions. All right, the quadratic function. Sometimes the authors might call this the squaring function. You might want to add that to your notes. I'll typically just call it the quadratic function. I think there's a type error on your notes too. This needs to be a bracket for the range. Okay, because the parent function does come down and touch the origin. All right, so this is just y equals x squared. Add the arrows if you want to show the domain and range continue. Here's the cubic function. F of x equals x cubed, or y equals x cubed. Takes on this shape. Okay, kind of just bends through the origin and then increases to the right. All right, the square root function. It's the last one on this page. It always starts at the origin, includes the origin. That's why there's brackets on these intervals over here. Continues that way. Okay, let's take a look at the next page. Reciprocal function. I just want to point out that there are asymptotes on this graph. Draw them in if you want to. Kind of put a dashed line, or maybe since if you have pencil and it's the same color, just make it dark. And there's also an asymptote along the x-axis. So both axes have an asymptote. So what does that mean? It means this part of the graph is going to get closer and closer and closer, but just run along that line. It's not going to cross over it. Same thing in this horizontal aspect. Okay. All right. And this is a way we can use interval notation to say x can equal 0. We can see the graph. It continues forever in this direction, forever in this direction, but there's a gap at 0. Okay, so make sure this makes sense. It's going to come up more and more. How do you get rid of a number using interval notation? Well, neg infinity up to 0. Remember, if I don't have a bracket, I'm not including that number. So parentheses means don't include 0. Now let's pick back up at 0, not including 0 again, and go to infinity. Okay, so a fancy way of saying x can equal 0 with interval notation. Okay, and the step function, we're going to deal with that on day 2. So let's just skip that for now. All right, so let's look at the directions on example 3 and 4. Name the type of function represented by this equation. Like I said, the parent function doesn't have the adding and subtracting and the multipliers. If we were absent of that, this would just be y equals x cubed, or f of x equals x cubed. So we call that the cubic function. Okay, so that's the first thing they're asking us to do. Just name it. Then we use a graphing utility to graph the function. Okay. So if you don't have a graphing calculator, you need to either find an app on your phone, either free or maybe you want to pay for it, or try this website, metacalculator.com. Those of you in class, I can show you on the web page, but at home you can't really see this until you get on this website. And then there's a graphing calculator little button to the middle left you hit, and then you can punch in the equations just like you would in a graphing calculator. Okay, so I'm going to use this for right now. I'll show you guys the website here though in just a second. Okay, so we have x cubed minus 2. Zoom 6 is usually a good starting point. All right, now I don't want you just to wing it. Just grab some good key points. You know, what's a good key point? How about these x and y intercepts? All right, and then maybe just a point down here to help me shape it. Just be smart about it, be reasonable, get some key points and add them to your graph. So if I hit the trace feature, it brings up this little spider where I can start getting these points. So 0, -2, there's my y-intercept, plot it. I'm going to trace along to get the x-intercept. Something close to around 1.2 or 1.3 is where the x-intercept is. Okay, so start by plotting those points. There they are. I got one more over here that just helps me with this bend. So I went over here and got this point around -1, -3.2. So -1, -3 approximately. Okay, and then we just kind of know the general shape of the cubic function, right? We're expecting you to know from the previous page what that looks like. Decreases, it kind of bends. The parent function bent through the origin, but it just got shifted. So bend it and then start to increase it again. That's it. Okay, you try it for 4. Just be careful on 4. When you punch this in your calculator, do not do this. Don't just put 2 divide x plus 3 like that without parentheses. Otherwise, it's going to treat it like this. If you want the plus 3 in the denominator, you have to use parentheses like this. Okay, so to get the right graph, punch it in the right way. And see if you can figure out the name of this one too. The parent function, that is. Go ahead. Okay, this is a reciprocal function, so that's what we should call it. The domain is x can equal -3, something you might want to think about, because when we go to the graph, we shouldn't see an x value at -3, right? Because when -3 is plugged in for x, we get 0 on the bottom, it's undefined. All right, so this is how I'm going to punch it in. And we get this reciprocal function right here. So at x equals -3, there's actually that vertical asymptote we talked about in the parent function, which your graph shouldn't hit. So I highly recommend you draw the vertical asymptote in your graph. Like this. That way your graph won't hit it. Okay, so I drew a dashed line at x equals -3. Let me zoom in so you can see a little better. There you go. All right, and how did I get that point? I just hit the trace feature again, right? I just hit trace, moved it along to find that bend, and then I'm good, because then I know it runs along the VA and vertical asymptote, and it runs along the x-axis here. So that point was -1.9 and 1.84, and I just estimated that. And then did the same thing down here, and draw these bends along the asymptotes. Okay. Okay, that's it here for today. We'll finish this section on day 2.